And we arrive to first order differential equation, which I now rewrite in the following evocative term. Well, eta is nothing but a rescaled stochastic force. Since I'm dividing by the m gamma that was standing in front of the accelerator, I'm rescaling the acceleration, I'm rescaling the random force to eta. And d is the so-called diffusion coefficient, which is defined to be kappa t over m gamma. So that's the Langevin equation. And we were sort of defining the Langevin equation in the attempt of answering the question, what is the probability distribution of dynamics? How can I sample the dynamics of the probability distribution in phase space, or in this case for the Langevin equation, where there's no momentum in the overdamped limit, we could talk about only configuration space in the overdamped limit. In the more general case in which I keep the acceleration, so the underdamped limit, I also have momentum and position, in which case the dynamics is defined in phase space. What is the probability, the dynamics of the probability density in phase space or in configuration space? In Hamiltonian system, we know this is the Deauville's equation. But now we want to obtain an analog result for this system where we have explicitly integrated out over the path. So the problem that motivated us towards developing the overdamp, the Langevin equation, was finding the dynamics of x and p as a function of t, probability distribution in phase space for the underdamped, so basically finding out what's the right hand side of this expression, or what's the right hand side of this expression if I am in the overdamped case. Because if I'm in the overdamped case, there is no momentum in the equations of motion, there's only velocity, and it's the first order differential equation. So I don't have a definition of a phase space distribution to begin with, only a configuration space distribution to begin with. And after having obtained the Langevin equation, we came up at least with a prescription to define this evolution in a practical way. You sample initial conditions from some initial distribution in phase space or configuration space. You solve the Langevin equations for each of these conditions. And you obtain a probability distribution after a time t. And that's a practical definition of your dynamics in phase space or configuration space in the overdamped limit. We want to do better. We want to find the equivalent of a Deauville's equation, the partial differential equation for P. We will postpone this problem by perhaps 2 lectures. Today we deal with some mathematical problem mostly. And today we discuss what is called the stochastic calculus. What is the stochastic calculus? So we discussed about functional calculus, Riemann's calculus, or standard calculus. And now we introduce yet another term, stochastic calculus. What is this object? Well, I will give a very physicist's sort of introduction to stochastic calculus. This is a very fascinating, modern, and quite complicated subject to be dealt in rigorous formal terms. In other words, this is a place where mathematicians can go wild and do their job. As physicists, we try to stick to sort of in a very sort of a crude, usefulness-oriented type of approach. And I am admittedly not an expert on the mathematical details involved in stochastic calculus and stochastic differentiation and all the conventions associated with it. I, of course, know a little bit. What I'm interested in is in the perhaps physical origin of this difference between ordinary calculus and stochastic calculus, and how to use that in practical applications of statistical mechanics. So I will keep this discussion as the most superficial and hand-waving possible level, apologizing to begin with whether I will be, by necessity and by ignorance, not particularly rigorous, or probably not rigorous at all in this discussion. So why do we need yet another calculus? Well, let me write the overdamped Langevin equation once more. Now, on the left-hand side is a time derivative. So the derivative on the left-hand side is the derivative of a function. One would expect this to be a smooth function. In physics, anything that is differentiable, anything that you take derivative of, is a smooth function. On the right-hand side, however, stochastic force, which is delta correlated. What do I mean by delta correlated? Again, I mean that they obey a fluctuation-dissipation relationship of this type. Now, I've explicitly used here the diffusion coefficients, and this is the fluctuation-dissipation theorem for eta and not for psi, so there's a rescaling of the factor on the right-hand side. Now, what does it mean that you have a delta correlated? That the value of the function at time t plus delta t, after I discretize this equation to level delta t, is completely uncorrelated to the value at time t because of this delta function. Remember, the physics of it was the bath loses memory instantaneously, and by instantaneously we meant within a time delta t whose inverse 1 over delta t frequency was above the cutoff frequency. So it's an ultraviolet scale. We are not resolving this. But see, this means that eta is never differentiable. In any point in time, there is no such a thing as a differential of eta. So if I were to draw eta in units of delta t, it would take any possible value with no particular relationship. And if I draw a different time series, it would look completely different with no particular resemblance. That's the notion of complete decorrelation. So the problem is that on the left-hand side I have a derivative, and on the right-hand side I have something that is never differentiable. Clearly, Riemann is not happy, nor is Newton, nor is any Leibniz, or any formal mathematical derivation of calculus we learn in first and second year in college. So clearly what we mean by derivative is something different than what we mean by derivative in the Newton's equations whenever we have a stochastic force. And that's, I think, quite important point. The mathematics that we are equipped with is not sufficient to describe stochastic processes with delta correlated noise. That's the conclusion we arrived. So what do? Well, remember, the general rule that I try to convince you is that of always discretize if you can. Meaning, whenever things don't make sense, take a deep breath, take a step back and write the discrete equivalent of whatever you're writing. Whatever error we're making by this discretization is above the cutoff, and we should not worry about that. It could be reincorporated by a rearrangement of the effective parameter below the cutoff. So what is so how do I rewrite the the Langevin equation in a discretized form? Well, it's a rule for evolving in time by configuration. The configuration at time t plus delta t minus the configuration at time delta t, that's the definition of velocity. But let me take the configuration at time t on the other side of the equation. So that these two terms come from the original x dot, let's see. Well, this is equal to negative d kt delta t grad u of x of t plus, and plus, then I have the stochastic force. Now the stochastic force here have an ambiguity, because you see I'm to the extent that I do not know, so to say, to the extent in which delta t is an ultraviolet scale, I could choose to have my stochastic force evaluated at any time between t and t plus delta t. Or if I want to be agnostic, in the most general case, I would have like an integral. What I should actually write is the integral for time delta t of the stochastic force. And now I want to discretize this integral, and I can do it in many ways. I can choose to define this to be delta t eta at ti, or delta t eta of ti plus delta t. Let me put an I here. Or in the middle, or use a Simpson rule. That's my convention, if you want, on how I define this integral. Now, when I take the limit, there's no difference at all, because they all give the same mathematical object. It's called the velocity. That's why I don't do this discussion for this term here, because this is a smooth function. But since this guy here is a completely different object, is a delta correlated stochastic variable, then of course the value I get if I do this here and the value I get if I do this are not related by continuity, unlike these two values here. At time t and t plus delta t, the error that I'm making is over delta t, and I don't care because there's another delta t here, because this is a smooth function. On the other hand, eta is never smooth. It's the most rugged object you can possibly think of. It's something that changes in a random way at any time scale. So the value that you get at these two time scales here and here are completely uncorrelated. And so you cannot simply say I can choose one or the other, it doesn't matter. You have to tell which one you're choosing. And depending which one you're choosing, you basically are giving a different definition of derivative from the left-hand side. So that's, if you want, the concept of stochastic differentiation. You need to define a rule because it's a differentiation that involves a stochastic variables that is delta correlated. Now, I am sure the mathematicians have a much deeper understanding of this, and they will probably give you a much better and detailed definition. But for the purposes of this course, this is good enough. I mean, I never needed any more in-depth understanding of this. I will need though some implications of this later on in the course, and we'll come to that later. So in particular, in this course, we provide what is called the Ito calculus. And the Ito calculus is one in which you discretize according to evaluate the stochastic function, the stochastic noise, at the initial time. So my function x of t plus delta t is equal to the function f of t, negative d over kt grad u of x of t plus eta of t delta t. And there's delta t here. So that's called the Ito derivative or Ito calculus. You can, like I said, define different objects. In particular, the Stratonovich calculus is another definition which is often used. And I don't think I even report the Stratonovich definition in the notes. I'm checking as I speak. I don't think I do that, so I will not discuss it here. The only thing that I want to say is that the Stratonovich definition is one in which I think you evaluate this as you don't evaluate this at the initial time, as a result of which this equation is not straightforward to solve, because you see the advantage of this equation is that it is so easy to solve because the right hand side depends only on things evaluated at time t, and the left hand side of this equation will give you the configuration at time t plus delta t. So this is really a Markovian type of process in which you define a system at time t, you throw a dice, define a sample from some distribution, the stochastic variable, and with that and the force and the previous condition, then you get a position at time x plus delta t. Then you throw another random number, get a new value for the stochastic variable eta, and evolve the system further from x t plus twice delta t, and so on and so forth. So you see, it's a Markovian process. What is a Markovian process? A Markov process is a stochastic process in which the configuration at time t plus delta t only depends on the configuration of time t. Is the system with the least memory. Now, the overdamped Langevin equation in Ito calculus defines a Markovian process in configuration space, while the underdamped Langevin equation defines a Markovian process in phase space. So in this sense, the Langevin dynamics defines a Markovian process. But one should bear in mind that the Langevin dynamic in the underdamped limit contains second derivative. That means that it depends on the function of time t minus delta t and t minus 2 delta t. You need two different times in order to define the derivative of a derivative. So it's not Markovian configuration space. However, if you rewrite it as a first-order differential equation in phase space, as we did, then it's Markovian in phase space. Because the momentum is basically defined out of the velocity, while the evolution of the momentum is defined out of the configuration at time t and the velocity at time t, plus the random noise at time t, if we choose the Ito calculus. Well, this is just at the moment, at this level, this is a mathematical discussion that might be interesting for some, but it seems to be sort of a curiosity for the level of the course you're taking up. We will see later on in this course that this is not actually the case, that the choice of calculus does enter in a massively important way when we work with integrals over stochastic variables. And in particular, we will discover that after we define the stochastic integral, we will learn that stochastic derivatives and stochastic integral are related by a fundamental theorem of calculus, which is not the same as that of the Riemann variables. And we will need this result to arrive to the correct path integral representation for the solution of the probability density evolution in a stochastic system obeying Langevin equation. So let's continue and define stochastic integration. And again, we define a stochastic derivative. Now we define a stochastic integral. It's called the Ito integral. And the Ito integral, let ft be a stochastic variable, a stochastic function. And the Ito integral is defined as the limit of delta t going to 0 in the physics sense, we should say, but that's the mathematical definition, so the mathematicians don't have this RG mainframe, of course. Then I have my usual Riemann sum. And then, rather than delta x, I have x at time t k plus 1 minus s of time tk times f of xk. Now, these variables here are variables generated according to a stochastic equation which contains stochastic noise in the Ito formula. So these are not just, any way, these are not arbitrarily chosen like they are in the Riemann calculus. Take an interval, take 2 points within the interval, then the function will be bounded by blah, blah, blah. The definition of continuity of a smooth function, of a function in general. Now, these distances are actually the result of integrating a time series by integrating stochastic equation of motion. So we're talking about something significantly different. And why is it different? Well, because you see, let's forget for a moment the fact that we have a random force. Because you see, let's go back to the Ito equation of motion. The position at time k plus 1 is equal to the position at time tk negative d delta t kt grad u of x of tk plus the random force at time tk delta t. We'll call this wk, the Wiener noise. In order to understand why the stochastic calculus is different from the ordinary calculus, and in particular why the stochastic fundamental theorem of calculus does not correspond exactly to the normal fundamental theorem of calculus, let us ask ourselves, what is the order of this difference which enters the definition of the Ito integral and we use to replace what in Riemann's integral would be delta x, right? So what is the order in delta t? Well, if I look at this difference here, I would be led to thinking, if I just look at the first line, that this is of order delta t. But it is actually not of order delta t once I allow the second line to be in the game. In fact, let's take this square root of this and take an average. Now, and for a moment, just for a moment, forget about this. Let's ignore it for a moment. And we will see later that we can do that provided the delta t is small. Well, if I ignore that, then this is basically the correlation function of my noise function. And basically, by applying this equation of motion, you discover that this is nothing but essentially eta tk, right? Delta t. But now let me remind you that the eta functions are delta correlated, which after I discretize this becomes, well, let me be more generous and put an I and j here. I and j. This becomes the Kroneker's delta divided by delta t. Why? Because this is a smeared representation of a delta function as a function of width delta and height 1 over delta t, because the volume has to be 1. Right, that's the delta correlation function, the fluctuation, the dissipation. This is the delta correlation expression, which basically means that this square here is of order 1 over delta, which in turn means that typically the root of a typical xt plus, let's write it in a slightly more tidy form. So what we arrive in to the conclusion is that typically, if I take x at time t plus 1, k plus 1, minus x of time tk, take the square, take the root to get something of the units of distances. This is of order roots of delta t. Why? Because the square is of order, this is of order 1 over delta t, this is of order delta t squared, so the square is of order delta t, and therefore the root of a square, that means the root mean square displacement, is of order root of t. That's why I could ignore this term, by the way. Why? Because if I take delta t small enough, then I'm dominated by the lowest power of delta t. And the lowest power of delta t in this equation is 1/2, not 1. So this is what is called a fractional calculus. And as you can see, fractional stochastic calculus is related to fractional derivatives and fractional calculus. So we are learning that unlike normal calculus, where the displacements are proportional with time intervals, because that means that you can define a velocity as smooth velocity. In stochastic functions, root of mean square displacements are proportional to root of time. And therefore, all the calculus is just completely different. And you can actually, at this point, jump ahead and give you a mathematics result, which I will not attempt to prove, but it's a general well-known result in stochastic problems, and it's the following. If I take the Ito integral from, say, t naught to t, and I take a function that depends on t through x, and I take the integral in dx, f prime of x, that's exactly what we were heading with before. So we want the fundamental theorem of calculus. So I'm computing the integral of a function that is a derivative of x over some time. X is a time series obtained by Ito rule. Then this object is equal to f at time t, so the final time, minus f at time t naught. And that would be the fundamental theorem of calculus. But there's an additional term, negative of d t naught t ds f double s of x of s. Well, this is a Riemann integral. So what we're discovering is that the fundamental theorem of calculus contains an additional term which depends on the diffusion coefficients d, and it basically is the integral of the Laplace of the second derivative of the function, and it's defined through a Riemann's integral. So the fundamental theorem of calculus for the Ito calculus contains the usual difference between the functions, plus one more integral over defined as a Riemann's integral. That means that, define it as a Riemann integral basically means that I can discretize and in whatever form I want, and I will get the same result. So this is the fundamental theorem of the stochastic calculus. And At this level, this is just a mathematical tool that we are introducing without particular evidence of why we need it. In the next lecture, we will see that this is actually quite a fundamental result that will come handy when we will have to define a path integral representation for the stochastic dynamics. So in the next lecture, I will begin by reviewing all this material and sort of enucleating out the part that we need to stick on, that has to stay in our mind, the take-home messages. All the mathematics details you can find in the notes. I apologize for not being completely transparent at some times, but this is the first time I give this course online. Giving a course online is significantly different than giving a course in front of an audience. Okay, said that, thank you. Bye.